Thanks. It's been very long. It's quite a time since I haven't presented anything at a conference, so it'd be nice for me. Yes, I would like to talk about constraint learning, about non-confluent systems, which kind of just means something similar to what we had just before, but in a slightly different way. And yeah, just to briefly recap for those people that just arrived. Connection calculus is just a version of circular control. It's similar to binary resolution. It's sum complete, it's store directed, and it is non-confluent. Oh my god, you have to do that. And you use iterative infinity and proof enumeration to do reasoning in connection calculus. Okay, I think you might have that's before. Before I was talking about connection matrices, which are a different view on connection tableaus. So connection tableaus and connection matrices are pretty much the same thing, even though in connection matrices you might have shorter proof because you can reuse the same clause instance multiple times. Whereas in connection tableau, which is really pretty much a third order tableau, you're not allowed to do that. It's pretty much really what you would expect if you're talking about a free variable tableau. There are three kinds of rules, and it's even easier than third order tableau if you know it, because we assume there are clauses. The first one is the so-called sign rule, which just means we take our clause, we put each literal on one of the branches. So it's just the same as if you would have in a third order tableau. You just apply the OR rule, the positive OR rule. Then we have a branch to just the literal. Okay, super. Then we have the reduction rule, which just means, if we have a literal on a branch somewhere, it's not closed yet, but we have a dual literal somewhere, which is a parent. So we're going upward until towards the root. But in between, we find somewhere a literal, there is dual, we can immediately close the branch here. And we have the extension rule, which just means we just take a new clause instance of our bag of clauses, add it, and at least one of these literals here that we add here has to be directly connected respectively dual to the literal that annotated this branch before. So this L1 here is dual to L. Well, then we can just do this extension step. And these are sufficient to be sound complete as we had it before. Okay, not really surprising. Let's take the example from before, but now in a tableauish way. First, we try the start rule, which just means the text with blue clause here. We could put one branch here, the B of set 1, and the right side, B of F of set 1. So, set 1 are of course shared, so we have a unifier that is local. And that is why we're doing right here. Just so far, this is the identity between that in set 1 and set 1, x1 and x1, and so on, and so on and so forth. Then we apply extension rules, which just means we take a new clause instance of this clause, C2, and we just add it here. This left clause here is not P of x1, is immediately dual with P of set 1 by adding a respective unifier. So we just make x1 now substitute with set 1. And we apply reduction rule by just applying unification here. Now you see this both moves here up close. Then we apply another extension step by taking another clause instance of this from here. So that's why here it's just x2 rather than x1. And we apply again some substitution and apply another reduction rule. And as you can see, all branches are closed, no open branch. It's like first of the tableau. Quite easy. Yeah, this is it. Cool. We are at Tableau, so if it would be a table, we would say, we have set solving, just recap, conflict learning, set solving, TBCL, and so on and so forth. We have a set of clauses here, so conjunction of disjunctions. First, if we don't know anything better, we just randomly assign some Boolean variable to values. So let's assume we assign A to 2. Okay, then this A will not become true anymore, but this clause now is satisfied. Cool. We don't know what to do better, so we just guess that 2 is true. Okay, this clause it was true before, but now it's even more true maybe. But yeah, now this first clause here, even if it sounds dangerous, if you now assign this C default as well, then this clause is not satisfied anymore. Well, so we propagate, so we like Boolean constraint propagation, Boolean propagation to say C is true. Okay, that's makes at least this clause not true. But now this looks dangerous. Okay, so we apply again Boolean constraint propagation and assign D true. Okay, both are true. First one, second clause, but the third one is not violated. Okay, well, we back jump and learn a new clause that kind of try to rule out this conflict by learning the dependencies of the assignments. So in this case, we learn when we shouldn't have assigned A to false, A to true, and B to true. So either A was be false or B was be false. We add this clause to our clause set and we just back jump and proceed. So that's all. I mean. And so far, what we have seen in the previous talk is we saw it might be a good idea to do content learning for connection calculus from more generally to that system, but we failed because of having a overhead when implementing set. And yes, although it wasn't really guided by anything, so what we came up with, well, let's create a new specialized learning engine for set solver. For connection calculus solvers that learn their clauses on the fly but still maintaining the usual connection calculus group enumeration approach. So how do it work? Well, let's consider an example. This one's a bit more tricky. Well, it's really close. You can see this four leads were already closed. There's always connection going upwards with dash one. Here as well, but this R of xy is not closed yet, so that's why it's not colored red here. And what we do is we maintain explicit positions. So in particular, well, here. So we can think these elements here are just the positions in the tree. So for example, we can explicitly pinpoint down any element here by just referring to its position. Already now have three different kinds of literals. So the first one is a start clause literal that just says, well, we put this particular clause here on the start. So we have, of course, only one of them assigned to true. Because, well, we only start once. So that's what we want. Rather than in the previous one where the set solver start having multiple proofs at the same time. Then we have reduction atoms. So in this case, it just says this element here at the position 1.2.2 is reduced to position 1, so it's this X here. And we have extension literals that say, well, here we go. That tell me, oh yeah, for example, this one here is at this position 1.2, we added this clause here, or in this case here, this not here of W is added at the position 1 here, that's right here, the 1, and this one here that refers to the position where we attach it to. And we just say a position I is open if we neither reduction or extension step to it. Okay, but very easy, I think. So now assume we have these two additional clauses in our clause set. Okay, yeah, that looks on the first, if you just look at it, it looks good because we have here this R, X, Y, we need to close it, and both of them are negative. It's pretty cool, so maybe we can close it this way. But unfortunately, we had some unification constraints already applied. So, for example, here this X is already bound to C because, well, this left part here, this right already B because of this part here. So we have actually an RCB. The problem is now it doesn't neither unify with the blue one or the pinkish one. So we have to now kind of justify why is there a conflict? Why can't we apply any extension reduction here? And the reason why we cannot apply an extension rule is, well, we cannot do an extension rule to this one with this one here because there is a C here in the RC. And why is there a C? Well, because of this whole left subfield here. So the reason for that is all the atoms that are responsible for having this subfield on the left side. This is mainly the reason why we have to see here. Similarly, you cannot apply extension with the valid one here. Well, because we have a Y human at the B, and the reason for that is this extension step here that kind of this subfield here. Okay, so what we do is we learn a certain clause that says either we don't even have this element here to close, the reason for that starting clause, the starting with clause that we just started with this clause here. Or, and it is maybe we just have to undo anything that kind of results in this being sealed here. So we have to undo anything that's broken. Or we have to undo the valid thing here. We have to undo this one. So we end up with this clause here. So we can just add it, yeah, we would rule out the something. Cool. And we even can observe something cool, namely that this is not entirely something trivial either. Let's go back. Here, you have this right part here. Here is some unification happening. This the set here. Well, we did something with the set, but in this conflict, as we see, well, there's nothing talking about the set. So what we learned is not entirely trivial. We could just learn, don't do this at all. But that's not what we learned. We learned something more strict. It's more something stronger. Maybe something that's not talking about set at all. So that's cool. Although, furthermore, all the clauses we learned are purely negative. There's nothing positive in them. Okay, it sounds like that. No, and all the decisions we made are purely positive. So we always say, oh, well, we do this, we do this, we do this, and we always run over the conflict with our purely negative clauses we learn. Furthermore, this kind of allows us really just to have a way of detecting conflicts. We just want to find out whether a clause is violated. We don't want to propagate anything as we would do so in sets, for example. In set, we would say, oh, everything but one literal is false already, so we have to propagate the last one. In our case, we just need to detect whether there is a conflict. And this is way easier to implement into so-called one-watch literal scheme rather than a two-watch literal. Furthermore, what we did is sound and complete and dominating for a fixed step limit. However, the contexts we learn are very specific to the proof we're currently considering. So that's not really good because going back here, it really depends very much on which exact steps we're taking rather than what's actually happening in the proof. Okay, so let's go back and let's refine our encoding a bit more. Well, we still maintain position, so I didn't change anything in the picture here, but we now only have two kinds of literals. Before we had, well, we have a start literal, we have an extension literal, a reduction literal, but actually, why do we need them? We actually don't care where the unification comes from, we just care that there is a unification that prevents us from doing so. So what we have is just a way of expressing, well, a certain clause, a literal instant is a certain position, so we annotate it by having this literal, so here x at 1, that means, well, at position 1, there is here x, for what a surprise, and we represent that certain variable bindings happen. For example, here, x was bound to w, or x was bound to c. We don't care where it comes from, whether it comes from an extension step or from a reduction step, we don't care. We just care, well, there is a certain binding. And the main difference to what we saw before is that we just don't care about this. So, go back to the example. We still have our two additional clauses that do not necessarily get an hour to extend this difference here. Well, again, you have the information that x is not to c and y to b, but we need to connect this RCP to something, but we cannot. So we have a weighting representation right now, right? It's just that, well, the reason is that x is matched to c, which prevents us from taking the blue clause here. And the y is matched to b, which prevents us from taking the second valid clause here. Okay, so the clause we learned is way easy now. We don't put the RXY here, no matter where it comes from, we don't care whether it came from a starting rule or from something else. Or don't put here where you don't have X to C, or don't put Y to do. Okay? But so far, I was making it slightly easier than it actually is. So far, as you can see, here we couldn't actually apply any reduction steps. This was purely about extension steps, but the reason for that is well, reduction steps are harder. But we have a solution for that. But let's consider a different example in which we don't care about extension steps. And so we already have this partial connection type for the 3 here. And we would like to express now that we cannot reduce to anything. So we have this here C, and apparently here this X was mapped to B, otherwise we wouldn't have allowed this extension step here. So this QFC could in theory reduce to this one, but not given the current method of the variable X. Furthermore, we definitely cannot unify with this or reduce to this one here at all, because here this is an R and this is a B. So yeah, forget it. So therefore, we have to express something like, well, here C, this one here, at position 1 or 2 by 2, where P, right? So we have to say, well, either don't put here C at position 1 or 2 by 2, or, well, we can't apply any of the extension steps, so that you can show you here, or don't put this P of X here, or don't allow X to bind to C, or don't put the R of this R of Y, R of Y here. But we might not ask, why do I care about this R of Y in position 1 or 2? I mean, there's no way to connect to it anyway. It's a completely different symbol. And in fact, it is completely irrelevant. But we need something as a placeholder to say, well, there shouldn't be anything that can be here that would be a candidate to reduce to, in the same, there is an R Y in this position, at least expressed though. But it's very specific, because we just want to say, well, it's nothing we can connect to. Whether it's an R of Y or an S or a T or a completely different symbol, doesn't matter at all. And this is what we all have to do, namely a so-called auxiliary symbol we use here, this single symbol here, that just says, well, the position Pi and the position Pj, they could in theory unify, they could in theory be connected. So what we can say is, well, now we can just say, yeah, don't put here C position, or we just be allowed to do it on extension step, or we don't put here with P of X, with the respective unification constraint, or, well, put here something that we could unify to. But so far, it's something we could unify to, because R of Y is something we can definitely unify to. So yeah, we implemented this in a now prototype for PopCop, and we again compared against our favorite enemy, so-called Mooncop. And this time, even with the cut operation, which makes it incomplete, but we always have here the complete version, second line. And we compared on a bunch of 2BPP and other benchmarks, of course, or theory benchmarks, and we see, well, it's better than before, right? I mean, we always proceed, we always win by far, apart from this benchmark set, but we are actually way better than Mooncop. So, cool, right? But it's even better. Looking at one example here, for example, in detail, let's take puzzle 5 of the 2BPP benchmark set. Yeah, and let's look here. You have the certain iterative scrutiny levels, such as stop it when reaching proofs of step 1, step 2, step 3, step 4. Of course, if you go deeper with the step, then you can apply more steps. And these are the steps are shown here that we apply the number of extension steps that the solver has to try out. And you see, yeah, Mooncop is pretty optimized. I mean, at first, it really optimized away a lot of potential extension steps. Which is good, yeah, we are bad, yeah, we feel bad. But then at some point, we're better. And the reason for that is that actually conflict learning really makes a difference. Conflict learning really rules out certain extension steps that Mooncop cannot rule out. Well, that's cool, and that also justifies why we are way better in the most proper benchmarks. And as a cool cherry on top, PopCop participated in this year's past competition, so the first of the theory improvement competition. And we were not last. We want to go first, right? I mean, I think it's a respectable result for a theory improver participated now at first time. So 88% out of the 500 that were given to us. I think that's not bad. So, of course, there's always a lot of things to improve. We're aware that there are certain things that we could definitely do. In particular, we were always talking about, yeah, don't do this particular assignment. Or conflict in case we do this assignment again. But why not just say X has to make this assignment, and then we just turn it up, turn it bottom up, and just say what we have to do, what you should not do. Well, we could. The problem is that this is very hard to track. So far, these are very simple steps we have to apply to just check where there is a conflict or some clause is violated. Doing this is way harder because we always have to check, is there still a way to unify? Is there still a way to unify? Every single step. However, the order would allow us to propagate consequences, so we would not necessarily only have negative clauses, but rather positive ones that tell us, now we have to unify, otherwise there will be a conflict. So that would be cool, but this is hard to implement. And even more, and not asking to implement, is to get completely rid of positions, and we're aware that we could do that. We can even learn the universally quantified clause. Well, there for all paths that you can consider, and for all other paths that are previously in this, so are prefix paths of this one, don't have literal not key at this position. And still have different to fail extending it. Well, we could do this, but it's even harder because now we have to check a violation of a quantified clause. So, okay, anyway, to summarize, well, we introduced two new languages that try to avoid the problem we were I was discussing in the previous talk. Now we have something that allows us to do kind of really good content learning based on positions in the tableau. And we implemented it in POPCOP, and the initial results are, let's say, promising. So yeah, this is now finally the end of the talks. And here we have another couple of